650,000 to 800,000 years. And we showed how the carbon dioxide concentrations and temperature were correlated. So you should remember the typical range of concentrations during those glacial and interglacial periods. But when we start talking about man-made climate change, we're looking at obviously much shorter timescales by comparison. So if I were to ask you, in terms of clarifying those timescales, was the carbon dioxide concentration in the atmosphere during the warmer interglacial periods higher or lower than during the cooler glacial periods? What's the answer? Was there more CO2 in the atmosphere during ice ages or less compared to the warmer interglacial periods? Less. Good. Okay. Now, if you were to look at the changes in carbon dioxide on a seasonal basis today, is there more carbon dioxide in the atmosphere in summertime or in wintertime? Okay.
Winter.
Why?
Because nobody knows photosynthesis.
Correct. Okay, good. We'll remind you of that point later. So, when we talk about evidence, we have to look at a number of different aspects. Mainly people look at emissions, how much, and the rate of emission, and they need to look at the relationship to temperature. That's the basic physical relationship we want to look at. And we know from laboratory studies that the more carbon dioxide in a flask for the same amount of radiation going into that flask, the higher the temperature inside that flask. It's pretty basic, but of course the Earth's atmosphere is a little bit more complicated than a simple container. We also need to look carefully at the data sources, because not all data sources are the same. They have different resolutions, different precisions, and some of them are not direct measurements of temperature or carbon dioxide. They're what we call proxies. So we have to be careful how we interpret those data, and also how much of the data there is, what locations, where in the atmosphere. We also have to remind ourselves, and we talked quite a bit about this, natural variation in the system. So you know a lot about the natural variation in terms of solar, as well as volcanic emissions, etc., etc. So we always have to take that into account, particularly when we're looking at the uncertainty, and in particular when we look at how they might impact extreme events. For example, climate change has been recently linked quite strongly to increase in extreme weather events, sea level rises, flooding, ice extent, natural forest fires, etc. And the question is, are these extreme events related to climate change? In other words, are they within the same distribution that we might see in the past compared to today at different temperatures, etc., etc. And of course that all leads to, finally, what is the uncertainty associated with these? The final one is much more complex, and we're certainly not going to be able to cover that in this course to any great degree. That's for other courses, but keep it in mind. So if you're familiar with the IPCC, way back in 2013, the IPCC, the Intergovernmental Panel on Climate Change, which is an international body for assessing science related to climate change, released this report, the AR5, the Fifth Assessment Report. It was authored by 250 of the world's leading scientists from 39 different countries. And briefly, it's a very long report, it stated that it is extremely likely that human influence has been the dominant cause of observed warming since the middle of the 20th century. And then the report goes on to describe the various cumulative effects, mainly of carbon dioxide emissions, on our atmospheric content, composition, and also the enhancement in temperature. So please have a read of the assessment report or the relevant sections. Of course, since then there have been various updates, one in 2014, etc. And effectively what they're simply doing is emphasizing and reinforcing what was said in that original report with a few minor changes, different ways of looking at, for example, radiative forcing, different ways of interpreting feedbacks, etc. But what they said was that there's been a further strengthening of the evidence for human influence on temperature at extremes. So that seems to be quite clear now. It's now very likely, so they use terms like highly likely, very likely, etc. It's now very likely that human influence has contributed to observed global changes in the frequency and intensity of daily temperature extremes since the middle of the 20th century. And lots of scientists are using these increased frequency of extreme weather events as a sort of a proxy or a warning of what's to come. They finish up by saying that it's likely that human influence has more than doubled the probability of occurrence of things like heat waves, particularly in the northern hemisphere. Okay, what is the current evidence that people look to? Well, effectively, remember that atmospheric concentrations have been changing since pre-industrial times, but what we need to do is look at the natural variation in those pre-industrial concentrations compared to post-industrial concentrations. And this data from the original AR4 actually only looked at data up to 2005. We've got a lot more data since then, but the conclusions still stand. So the atmospheric concentrations of CO2 and methane, shown on the left there, far exceed the natural range over the last 650,000 years. So that's just a reminder from previous lectures what the CO2 concentration did over the last 800,000 years, but certainly over 650,000 years where we have the best data, you can see that the typical range of carbon dioxide is from about 180 to 200 parts per million up to 280, maybe 300 parts per million at best. So in other words, the range has only been about 100 parts per million. So that's the natural cycle, if you like, over that almost million-year period. So that's the sort of range we should expect. But of course today, and today we mean 2005 when this report was submitted, you can see that the concentrations far exceed the past changes, natural changes, and the natural ranges, at least over the last 650,000 years, probably 800,000 years. What have those changes been due to? Well, obviously the main ones have been due to, when it comes to CO2, mainly due to fossil fuel use. There is a second, smaller but significant contribution to CO2 increase from land use change. So it's very likely that the CO2 increases have been due to man-made emissions. If we move back to methane, you can see that again there's a very large increase in methane concentrations after the Industrial Revolution, around about 1750 onwards. And again, it's very likely that those increases in methane have been man-made. They're predominantly due to agricultural use, but also due to fossil fuel use as well. And of course, the third most potent greenhouse gas, in terms of direct radiative forcing, is nitrous oxide. And again, we see a similar increase after the Industrial Revolution. And those increases in N2O, concentrations are much, much lower compared to the other two gases, as you can see. Those increases are again primarily due to agriculture. So if we look at those periods there on the graph, which go back to about 10,000 years, just to cover the period over which man has been relatively active in terms of agricultural use, etc., you can see that between the 18th and 19th century, which spans the Industrial Revolution, the CO2 concentrations are starting to increase. During the Industrial Revolution period, CO2 concentrations were actually only a small fraction of current levels. They were around about 3 to 7 million tonnes in terms of CO2 emissions per year. By the 19th century, CO2 emissions rose to about 54 million tonnes per year. That's the estimate for about 1850. At the moment, around about 2018, 2017, we emitted around about 8,000 million tonnes per year. So the emissions during these periods were a very tiny fraction of what we are emitting today. And the numbers to bear in mind are pre-industrial concentrations of CO2 were the order of 280 parts per million. In 2005, and this report was, which is referred to in this 2013 report, the concentrations had only gone up to only 379 parts per million. Does anybody know what they are today? Perhaps a number you should all be checking every so often on the news websites. There was a famous landmark that was exceeded last year. It was in all the news. Somebody like to give me a number? It's on the scale there.
400.
Yes. So landmark global average temperature was exceeded last year of 400 parts per million. In other words, it's still going up. And in fact, this year, they're potentially worried that it might actually exceed 408, 409 parts per million. Now, at the same time, there's another worrying aspect to that trend, which I think is hard to see on that scale because of the long time history that's being shown there. And that is the growth rate of carbon dioxide. Now, the annual concentration growth rate, the rate of change of CO2, was larger during the decade prior to this graph, so 2005 to 1995, than at any time previously. The average rate of change of CO2 between 1995 and 2005 was 1.9 parts per million per year. So we're approaching 2 parts per million per year. So that's bigger than it's been since continuous measurements have been made on planet Earth since around about 1960. If we actually look at the entire period when those measurements started, 1960 to 2005, the growth rate was less, obviously. It's around about 1.4 parts per million. But it doesn't really matter how far back you go to when those very detailed measurements started. You can keep changing the averaging time. What it seems to show is that the CO2 concentrations are, the rate of change of CO2 in the atmosphere seems to be accelerating. However, there is year-to-year variability in those growth rates because of the way fossil fuel is burned, access, political issues, etc., etc. So there are discontinuities in the details of those growth rates. If we look at methane now, pre-industrial period, we're looking at about 715 parts per billion, much less obviously than CO2. But remember, methane has a significantly larger absorption cross-section, so it's still a potent contributor to greenhouse warming in general. And the way we can assess the contribution between those two gases is looking at this right-hand scale, which we'll come back to next week. You'll notice basically the zero here corresponds to the just before the pre-industrial period. The scale here is in watts per meter, and this is the radiative forcing associated with the concentration. And you can see that by 2005 we were above 1.5 watts per meter squared. Remember, that's global average. If we look at the radiative forcing associated with methane concentrations, we're looking at around about 0.4 to 0.5 watts per meter squared by 2005. So significantly smaller, but look at the concentrations, much, much smaller. It's quite a significant contributor. N2O, much smaller concentrations, but of course N2O is a very interesting gas. It's got an even larger absorption cross-section, but it's between about 0.1 and 0.15, maybe up to 0.2 watts per meter squared in terms of the radiative forcing. So pre-industrial to 2005, there was a 35% increase in CO2, and that's shown here, along with the accelerating rate of change of CO2. For methane, it was a 142% increase. For N2O, it's only about 18%. N2O is mainly agricultural related. And of course, the data is continuously updated now, so one always has to keep an eye on it. And this shows the detailed measurements from 1958 to 2018 at the Mauna Loa station in Hawaii, which is the main station, background station in the Northern Hemisphere. So again, we said 400 ppm a year ago, but remember that's just one station, it's not the global average. But you can see we're now approaching 410 parts per million. And again, that question when I asked you about the seasonal variation, you can see around about April, May, summertime, the concentration is typically above average compared to winter time. And as somebody said, that's simply due to the fact that you've got more vegetation during summertime. Vegetation, plants, etc. take in carbon dioxide through photosynthesis and convert that energy into biomass. So that's a way of removing carbon dioxide from the atmosphere. During winter, plant life goes into senescence, leaves fall off trees. What happens then? Well, first of all, the plants are not taking CO2 out of the atmosphere, but something else is putting CO2 into the atmosphere during that period. Plant decay is caused by microbes. Microbes, as they eat up all that vegetation during the winter time mainly, they tend to respire and emit CO2 into the atmosphere. So that's why you see the seasonal variation. And you'll notice this zigzag pattern here, those are the seasonal variations. And you'll notice the amplitude. It doesn't change very much over the entire period. Remember, this is in the Northern Hemisphere. So that's a natural variation, a natural annual cycle, but it's the blue line, the trend, that we're more concerned about. So, just to recap, the atmospheric concentrations of CO2, methane and N2O far exceed the natural range over the last at least 650,000 years, probably 800,000. Increases in CO2 are due to fossil fuel usage, we'll come to that in the latter part of the course, with land use change, deforestation, etc., providing another significant smaller contribution. It's likely the observed increase in methane concentration is predominantly due to agriculture and fossil fuel use. Methane, for example, is used obviously as a natural gas. The increase in N2O concentration is also due to agriculture changes, mainly fertilizers. One of the things we haven't mentioned is, of course, the lifetimes of these three gases in the atmosphere. Due to the way in which they interact chemically in the atmosphere, they have different lifetimes. Nitrous oxide, for example, is relatively inert and would stay in the atmosphere for around about 120 years before moving into the higher atmosphere, the stratosphere, where it ultimately interacts and destroys ozone, for example. Gases like CO2 have a longer lifetime, at least 30 years, and similarly for methane, although methane is typically around about 12 years due to the various chemical reactions it's involved in. So we have to take into account the lifetimes of these gases as well, which affects their net radiative forcing. So those are the things we've just gone over. Make sure you're familiar with these fairly basic numbers in terms of CO2 increases pre and post-industrial revolution and the rates of change. Similarly for methane and also for N2O. So those are the three basic gases you should be familiar with. And of course we keep updating these numbers. For example, in 2017 N2O had increased to 328 parts per billion, for example. And I would always advise you to look at the websites that shall we say, have a good reputation for data quality management, control. They look carefully at the data, so any websites involving NASA, any websites involving NOAA that actually monitor and model climate change and use this sort of data, those are the sites you should go to get your information. So that was the update for the class of 2017. Simply show the continuous increase in CO2, continuous increase in nitrous oxide. Methane is an interesting one. There was some hiatus in the growth rate, as you can see, between 2000 and 2005. And there are lots of arguments over what that is, and if you want to find out more about that, try and do one of Dr. Grant Allen's projects, and he'll explain all that to you in detail. But effectively there's an argument over whether or not it's a sink or whether or not it's due to a decrease in leakage rate, particularly in the ex-Soviet Union, in terms of the gas rigs, etc. But now you can see that it's starting to increase again in line with CO2. So I think we've already said this, but just to recap, very roughly since 1750, about 2/3 of anthropogenic CO2 emissions have come from fossil fuel burning, about 1/3 from land use change. 45% of that CO2 has remained in the atmosphere since it was emitted, and that's key in terms of the lifetime. 30% has been taken up by the oceans, it's thought, although there's still some uncertainty associated with that. The remainder has been taken up by the biosphere. About half of the carbon dioxide emissions to the atmosphere is removed over about 30 years. A further 30% is removed within a few centuries. So that's the sort of time scale you have to think about. The remaining 20% will stay in the atmosphere for a long, long time. So what we emitted 30 years ago is essentially still going to have a big impact today. And that's what people tend to forget. And when we discuss the impacts of carbon dioxide concentrations in the atmosphere, there are sort of 4 states that people refer to in a lot of these AR reports. For example, we always refer to the pre-industrial levels, about 280 parts per million. So that's a number you should remember. Then there's current, 400 to 410 parts per million. And that's mainly due to human activity. And on average, what we can say is that that increased CO2 seems to have corresponded to an above average temperature compared to pre-industrial levels of around about 0.85 degrees C. It was about 0.6 degrees when that 2013 report came out, but this report says it's a little bit larger. And that, as we said, has caused increased severe weather events and temperature, and also large changes in precipitation patterns. And as we said, climate scientists are now describing those anomalies as early signs of the destabilization of the climate, although that might be a little bit alarmist, but those words have been used. Now, back to the retention time of CO2 in the atmosphere. It takes a long time to get it out of the atmosphere, and basically, even if we were to stop emitting carbon dioxide completely right now, temperatures would still rise at least half a degree, probably 0.8 degrees C, above the previous increase of 0.85 degrees C that we've already seen. And that's due to the cumulative effects already in the atmosphere. So again, look at the IPCC report, which discusses that in more detail. Again, some people talk about this scenario, 450 parts per million, which is referred to as high risk. I'll leave you to look at the IPCC report to see what that implies. There are also other organisations like the OECD, which produces an environmental outlook report. So they produced one looking at what was going to happen up to about 2050, and they summarise the findings based on IPCC and other reports in terms of predictions of climate scientists and climate models. And they say we have a 50% chance of stabilising the average global temperature at 2 degrees centigrade. Not great compared to the pre-industrial period if we keep concentrations of CO2 under 450 parts per million. Well, we're only just over 40 parts per million away from that target, and we're increasing at a rate of at least 1.92 parts per million per year. So think about the timescales. Various reports suggest that, in their words, our current rate of fossil fuel usage will mean that we're going to exceed that 450 parts per million limit by around 2034. Some people say earlier, some people say a bit later, depending upon changes in our energy usage. Okay, let's look at some of these sources of these gases. Let's start with methane. And when we talk about methane sources, we have to split them into two different sources. One is called biogenic, and the other is called thermogenic. So the biogenic is on the left, the thermogenic is on the right. And what are the biogenic? Well, of course, we get natural emissions from wetlands due to bacterial, etc. Production, which are quite extensive, particularly in the far northern hemisphere, but also in tropical regions. And of course, we've also got seepage from landfills. And of course, we've got a lot of emissions from agriculture. And the thermogenic, and typically it's thought that those sources contribute around about 55 to 70% of the total methane budget. What are these thermogenic methane sources? Well, effectively they're anthropogenic sources, and what those are essentially seepage from coal mines, so it's geological seepage from drilling in mines. It's also leakage from power stations, and it's also leakage from oil rigs or gas rigs, and that contributes around about 30 to 45% of the global methane sources. And we can actually identify between those two sources by simply making measurements in the atmosphere of the isotopic ratio. Now, naturally occurring methane, seepage, which is a thermogenic source, has a very different isotopic ratio compared to the other sources. So we can use those ratios to identify effectively where the emissions are coming from. And that's one way we can use to split methane concentrations in the atmosphere between those two different types of sources. So, as it says at the bottom there, methane produced from biogenic sources contains actually much less carbon-13 isotopes, the heavier isotope, than does methane from the thermogenic sources. Those are the ones associated with fossil fuel extraction, fracking, etc., etc. So that's the way people here, such as including Dr. Grant Allen here, actually can discriminate between the different sources. So that's quite easy to do, or relatively easy to do. I shouldn't say easy. Now, the numbers here are approximate. You can see there's quite a range of uncertainty in those numbers there. And that's because there are still a lot of arguments over what the actual sources and, in particular, the sinks of methane are. But typically that's what the contributions are from those different sources. As we said, globally average concentrations of methane are continuing to rise along with CO2, and in fact accurately accounting for those sources and their relative contributions is still a key challenge in climate science. And if you're interested in doing projects associated with that, as I said, speak to Dr. Grant Allen. There's a lot of work that's been done in terms of looking at so-called carbon isotope fingerprint, which are used to identify different sources. So if you could measure the carbon isotope, you can then basically go to these databases and see what are the likely sources. And that again suggests that methane emissions with fossil fuel use and production, more recent data, suggests that maybe it's even larger than we thought previously. Some people think as high as 60%, some people maybe only 20%. But that's a sort of range of uncertainty which requires yet more scientific work. And again, you can read about those uncertainties and how we have these issues of balancing the methane budget in this letter written by Dr. Grant Allen in Biogeochemistry Nature. So if you're interested, have a look at that. Okay. Now we're talking a little bit about climate change in terms of radiative forcing here. We need to look at that in a little bit more detail. And when we talk about that, we always talk about what's called the equilibrium climate sensitivity. And that's essentially a measure of how the climate responds to a sustained climate forcing. You know, shining a torch on a little flask full of CO2 is a good way to think about it. That's a sustained forcing, if you like. But we typically define it as the equilibrium global average surface warming following a specific increase in CO2 over the initial concentration. Normally, it's the doubling of carbon dioxide. So we compare the rate of forcing between previous concentration versus a doubling of that concentration. And we'll write down the equation for that starting next week. Of course, these assessment reports continue to progress. And as I said, they suggest now that climate sensitivity is likely to be in the range of 2 to 4.5 degrees C, or at least they did in 2013 in terms of the third assessment report of TAR. It turns out that this number has now gone down a little bit. The best estimate then was about 3 degrees C. It's now around about maybe 2, 2.5. And it's very unlikely to be less than 1.5 degrees C, which is still probably quite true based on the recent reports. Some values substantially higher than 4.5 degrees C were predicted by some models, and whereas they can't be completely excluded, the agreement of those models with the latest models is not particularly good, so that number is basically an upper limit, if you like. Another thing we have to be aware of when we talk about climate sensitivity in response to increased CO2 concentrations, for example, is that there are lots of feedbacks. Some of those feedbacks, as we'll see, can amplify the greenhouse effect, but they can also dampen the response based on a direct forcing. And we always have to remember that the direct emission of water vapor, which is a very potent greenhouse gas, by, for example, human activities, is also needs to be taken into consideration. However, strictly speaking, it's not a direct forcing, which we'll explain later. And we're going to assume that human activities in terms of water vapor emissions is negligible, so it's not going to contribute to that net range of forcing you see in the IPCC reports. So it's important to remember as global average temperatures increase, as we mentioned in previous lectures, tropospheric water vapor concentrations have also got to increase due to increased evaporation, followed by precipitation after transport. And this is what we call a key positive feedback, because more water vapor increase is a positive feedback in terms of the greenhouse effect. But it's not what we call a forcing of climate change. Okay? It's not one of the CO2 direct forcings. It's a key positive feedback. So, again, water vapour changes represent the largest feedback affecting what we call the equilibrium climate sensitivity. But we now understand that extremely well, even since the third assessment report. And as we also mentioned when we talked about the Vocals project and the impact of clouds, cloud feedback still remain the largest source of uncertainty compared to CO2, methane, etc., because they can potentially cool the planet. Another issue, of course, is that spatial patterns of climate response are largely controlled by not just climate processes, as we saw with ENSO, but also by these feedbacks. For example, we can get significant changes in sea ice cover. Sea ice albedo feedbacks tend to enhance the high latitude response compared to the equatorial regions. So again, have a look at the content in the AR5 that talks about that. Warming, remember, is going to reduce the terrestrial and ocean uptake in general of atmospheric CO2. That means the more CO2 we emit, the more of these anthropogenic emissions are going to remain in the atmosphere. And that's what we call a positive carbon cycle feedback, leading to increased CO2 in the atmosphere. And that, of course, is going to lead to a greater climate change for a given emission scenario. However, the strength of that feedback does change depending upon which model you look at. So again, there's uncertainty associated with that we need to think about. Okay. Now again, we've already talked about this or alluded to this, but data sources are extremely important, and it's important we continue to collect those data. So the main one, in terms of going back through our 10,000 years, 650,000 years, are of course ice cores. And since about 1957, we have been making continuous measurements of atmospheric CO2, for example at Mauna Loa, but prior to that, we have to rely on ice core data. Most of that comes from Antarctica, although there is now more and more coming from Greenland. But at no time during the last 650,000 years has the atmospheric CO2, based on analysis of all those little gas bubbles trapped in these ice cores as a function of depth, at no time during the last 650,000 years, probably 800,000 years, has the CO2 exceeded 300 parts per million. That's just to emphasize the increase over the last 10,000 years, and specifically after the Industrial Revolution. 35% increase in CO2 following the 280 parts per million pre-Industrial Revolution concentration. That arrow there is actually pointing to some of the ice core data we see here in blue and purple. Those are mainly from the Vostok ice core and similar ice core sources in Antarctica. Of course, those ice core data are still being collected today because they're extremely useful for comparing with what we call proxy climate change data, and we'll come to those in a little bit. I just wanted to go back to this continuous measurement trace we saw from Mauna Loa in Hawaii. We started around about 1958, etc. So certainly after 1960 we have extremely high quality data, and the number of stations has increased significantly since then to the present day, to give us a nice spatial pattern in terms of the concentrations in both north and southern hemisphere, over the ocean, in remote locations, as well as locations closer to strong emission sources. And again, I just wanted to emphasize why the concentrations go up and down, which somebody correctly answered. Remember, the Earth breathes in during the northern spring summer and out during the northern autumn winter, with CO2 peaking around about May time. But remember, the amplitude of these is extremely small compared to the overall increasing trend in CO2. But remember, this is in the northern hemisphere. If we were to look at this trace in the southern hemisphere, because there's less vegetation generally, the amplitude of that trace would be much smaller. Peak to peak concentrations changes are much smaller. And this is just a rough example of a few years ago where all these various stations were. So Mauna Loa, which you can barely see on this colour scale, is here. And then of course we had one in the southern hemisphere, Samoa, Cape Grim, South Pole, the McMurdo Station, Palmer Station, and also in Europe, as well as in Trinidad, for example. And of course there's even one up in the Arctic at the Alert Station. But the number has increased even over the last 5 to 10 years as instrumentation has become cheaper, more efficient and precise. And as we mentioned, the CO2 concentrations are continuously being updated. You've already seen this graph. So this, for example, was around about 2015, and you can see that that trend is more or less steady. If in fact it's actually accelerating. The vertical scale is from 310 notice up to about 400. So this was the one that sort of got everybody's attention. You notice in that year it actually peaked at 400 parts per million, although the mean in the Northern Hemisphere didn't go up to 400 parts per million until a year or two later. Again, just to put that previous graph in context, that is the previous 800,000 years of CO2 compared to the current value of Mauna Loa. And the question is that concentration change significant? Most people would say it is. The question is, what is the impact? And using that sort of data and the rate of increase and the fuel usage that we currently know about, various people have made projections about how far those concentrations are going to increase over the next decade and even up to the end of the century. Again, these are highly uncertain, but if you look, for example, at the Mauna Loa, this report came out around about 2000 and I think this was 2010. The Mauna Loa concentrations are in here, so certainly well below the 400. This 2015 report basically was predicting that by the end of this century the concentrations would exceed 650 parts per million at current energy usage and emission rates. The various colours refer to the different ice core data. Again, some people might think that concentration prediction is alarmist, but it's something we have to think about. And again, if you looked at those previous graphs, we said CO2 concentrations to 2005 had increased by 35% since 1750. Now the numbers are around about 39%. And there is some evidence to suggest that these concentrations have never reached this level, even as far back as 20 million years. And of course the composition of the atmosphere was very different, so possibly not applicable to our current discussion. And we know that most of this CO2 in the atmosphere is from man-made emissions due to the isotopic concentrations, which is very different to the background atmospheric CO2. And again, in 2015 it was estimated 75% of the anthropogenic man-made emissions of CO2 during the past 20 years, when that report was read, was from fossil fuel burning. The remainder, 25% or so, was from land use changes and deforestation. So see, these numbers we're quoting here vary as we go from one report to another. So there is a range of uncertainty, but there are always big positive numbers. Okay. Again, I refer you to the third and fourth assessment reports. Make sure you read that. You don't need to read all of it. You can download it from that website there. I assume it's still active. They probably may have updated, but you'll easily find it by Googling IPCC, AR, or assessment reports. And notice when that original report was made, they were talking about 0.6 degrees C. Now they're talking 0.85 degrees C, based over the last 5 years of data added to that. They also mentioned that between 1995 and 2006 we had the warmest 12 years on record since 1850. that record has been broken. The warmest records were a couple of years ago, depending upon which institute's analysis you look at. And about half the temperature change since 1800 has occurred since 1800, and that's still true. So, what we can say is that the evidence for climate change is growing. It's evolving as we become more experienced, as we learn about its effects, and we can bring more technological innovations to bear on analysing the atmosphere to monitor climate change. And in every single case, criticisms of the scientific process in terms of analysing this data has been withstood. There have been discrepancies in these reports, but they've always been resolved to the point where the overwhelming majority of scientists accept the results that anthropogenic emissions are implicated in the enhanced so-called greenhouse or man-made greenhouse effect. And these effects are now observed globally and at all levels in the atmosphere, certainly the troposphere. Okay, we'll have to continue with this next lecture, where we're going to finish off looking at some of the more recent analyses of the evidence of climate change, and then we'll talk about the radiative forcing equations and how to interpret those when we're comparing different greenhouse gas contributions. So we'll start here next week. Thanks very much for coming. And again, if you know anybody who can't come to the lectures, I know one or two of you are still asking about podcasts. Because we changed lecture theatres, IT services unfortunately put the later podcasts into a different folder on their website. So that might be a bit confusing. All the podcasts are there, you just have to look for them. Somebody got the card reader? Oh. Thank you very much. One of my colleagues lost his. Somebody walked off with